thing here. Welcome back, everybody. As we discussed on Monday, the topic for this week is to kind of summarize many of the different aspects of oscillations, driven oscillations, because this is a phenomena in physics and in science, which you are going to meet in many, many different places. When you're moving into quantum physics, you're going to meet oscillations again. The harmonic oscillator is one of the standard approximations for a potential well. We are going to meet oscillations in electromagnetism. For those of you doing electronics or optics, oscillations are actually a kind of a daily, almost a daily bread. It's things which you would deal with on a daily basis if you're dealing with electronics. So the thing I want to do today is to summarize some of these things. And then there is a topic which I think is very, very nice, and which you will also meet more and more when you take physics courses, whether you're doing mathematical physics or electromagnetism or quantum physics. This is something which you will not meet in exercises. It's a kind of a small aside. That's an important aside. And it's a beautiful theory, and that's the theory of Fourier transformations, which is a way to represent forces which apply to a given system in terms of an expansions of cosines and sines. So if you have a periodic force which apply to a system, but this may not look like a sine or cosine, because in many cases you cannot make such things, but it could be represented by a function which looks like or goes like x, or x times something. You can actually represent this in terms of sines and cosines if it is a periodic function. So if something which gets repeated in a periodic way, you have a very powerful way to represent it by Fourier transforms. And Fourier's theorem says that you can actually expand a periodic function in a basis of sine and cosine functions. So that becomes an extremely handy calculational and computational basis. There is actually a very, or how to say, a widely used algorithm, which is called fast Fourier transforms, which some of you may have encountered, and it's considered as one of the top 10 algorithms in computational mathematics. So this is the topic about Fourier applications and to harmonic oscillations is a kind of an aside, but I wanted to have it, to present it here, to have it as a kind of teaser, because it's an extremely useful tool, which many of you will encounter and use again and again and again. But let's try to summarize what we did on Monday with these factors which we introduced when we looked at the width of the specific or the particular solution. So this particular solution has an amplitude, and this amplitude has a width, which is then proportional to the physical quantities of the system. So let's take a look at that. And then we're also going to jump into another example, which is the mathematical pendulum, which you will encounter in homework number 7. And that's a case where you're going to explore different parameters for the mathematical pendulum, which again is a kind of oscillatory motion. So let's take a look at the, go back to the whiteboard. So let me just stop sharing here. So on Monday, we looked at the differential equation for harmonic oscillations. So let me just bring it back again. So we have this famous equation now. We have the acceleration here. It's still in one dimension. And then we had a resistance or friction term, which was given by the velocity. And then we have this linear term in x, k times x. And then we had some applied external force here, F0 times a cosine. And we were able to find the particular solution to this quantity. So what we found is that the particular solution as a function of this dimensionless time, so I'm just quickly repeating what we did, was given in terms of an amplitude and multiplied by a cosine. And we had this dimensionless frequency and dimensionless time minus a phase shift. Now, this quantity d for this specific case, so keep in mind that this is something which now applies to this specific case. So what we had is that this function d is something which we rewrote in terms of this f tilde, and it was given by a denominator which has 1 minus omega tilde squared omega plus 4 times omega tilde squared and a parameter gamma. So I'm going to repeat some of these parameters because it's always easy to get lost in the jungle of parameters. So this parameter gamma was something which we defined as b divided by 2m divided by the natural frequency of the system. And this natural frequency was given by this constant k divided by the mass of the system. We defined a new parameter as well, which we called for parameter beta, which was simply given by the this friction parameter or resistance parameter divided by 2 times m. That means that this parameter gamma can actually be rewritten in terms of this term beta divided by omega 0. So I'm just doing this to bring back the link with what you may see in Taylor's textbook. So Taylor is using this parameter beta. Now, one of the things which we looked at then, and under the assumption that beta is normally much smaller than omega 0, which is a pretty common case when you're looking at experimental setups for different types of systems. Then what we had is that the maximum amplitude is something which we have when we have a frequency of the applied force, which is equal to the natural frequency of the system. The natural frequency is something which is given by the physical parameters which define the system we have. This means that we would then find that this D max is then given by this parameter F0 tilde, and we could rewrite it in terms of a, so let's just bring back what we did. This is basically where we ended on Monday. And I think we just went back to F. It's not F tilde here. So let me just correct that. F0 times 2 times this parameter beta times omega 0. And then depending on the value of beta, we could make this peak where we have the maximum value for the applied force. So the solution then has a peak. When this beta becomes smaller and smaller, that means that the amplitude will become larger and larger. So one of the typical things which we looked at last time was then to plot the maximum solution as a function of the frequency omega. So we would typically see something like this, a sharp peak here. And this peak depends on the value of beta and omega 0. And the typical situation which you have is that beta is normally smaller or even much smaller than omega 0. So the depending on the value, you could get curves like this. It would be more smeared out. So in this particular case, you would have something, this is just an example. You could have a beta, which could be equal to, let's say, 0.3 times omega 0. When it gets sharper here, you could get a beta, which is equal to 0.1 times omega 0, and so on and so on. So ideally, in many of these applications, we would like to have a very sharp peak. And this is normally called a resonance. The other thing we saw is that we have the half width. So half of the value for Dmax is something which is constrained into an interval, and it's easy to calculate one. So if you take omega 0, and if you take an interval which goes from omega 0 plus beta and omega 0 minus beta, what we would have then is an amplitude as a function of omega on the x-axis here. So if we have a peak up here, then here we would have half the value. And this kind of distance becomes a 2 beta. So this is half the amplitude. So one quantity which you will encounter in many textbooks and also in the literature is something which we call the quality factor. So you can actually rewrite your differential equation in terms of this parameter Q. So this Q is then defined by omega 0 divided by 2 times beta. So a large Q means that you have a narrow resonance. So when you're tuning in your radio to a specific frequency, you would actually like to hit that specific frequency. And you would then, ideally, you would then achieve a clear sound from your radio. There would be no kind of noise and disturbance in your radio signal. So ideally, when you're tuning in a frequency, then you're trying to make this resonance or this peak sharper and sharper around a specific frequency. So this quantity is called a quality factor. So if I take some examples, and these examples are taken from the textbook of Taylor. So if you look at Q values, this is typically 100 for classical grandfather clock. If you take a quartz crystal, in order to use that one to define a second, so this is typically a quartz crystal. So let me just bring that up. So this is one of the reasons why we use these quartz crystals to define precise clocks, because that means that if this Q becomes larger and larger, then this resonance top here will become sharper and sharper. And this is ideally what we would like to have. This means that we can rewrite the differential equation in terms of this Q value. So if we now look back at the equation which we had in the beginning here, so let's just scroll up a little bit. If you look at the equation, you can now rewrite this in terms of this Q factor. And one of the things which we also did was to introduce a dimensionless time. So let me just quickly remind you of that. So we introduced a dimensionless time, which was given by this natural frequency times time. Then we could rewrite the differential equation as a d of tau. And we had a factor of 2 gamma of dx d tau plus x, and that was given by this f0 of cosine of omega tilde times tau. This is the external force. And now with Q equal to these parameters omega 0 divided by 2 beta, you can actually show that 1 over Q is equal to 2 times gamma. It's actually pretty easy to show that by just combining these parameters. And you will see this equation here in many textbooks written in the following form: plus 1 over Q of dx d tau plus x is equal to f of cosine of omega tilde times tau. And often you would simply rewrite this in terms of a force of f of tau. This is a pretty common way of rewriting this equation here. We don't need to have a cosine something. We looked at this cosine as a special case, but you could actually have different types of applied forces. It doesn't need to be a sinus curve, it doesn't need to be a cosine, but it could be a square signal, which we are going to come back to this pretty soon now. Now, the reason why this is an interesting quantity is actually that the solution, or the damping of a solution, damping is given by, and you may remember this by this term e to the minus gamma times tau. And then depending on the value of this gamma, we could have a kind of sinus-like oscillation with damping, or we could get into a situation where we had critical damping, or overcritical damping. But in general, the damping part is governed by this parameter gamma. And what you see then, if we now reintroduce this parameter Q, this would now be given by something which runs like 1 over this parameter Q times tau. So I'm going to just ask you one thing. Have you seen some equations in physics which are governed by, so we've been looking at the decay due to damping, but we have other important physical processes which are governed by such an exponential. So when you guys took modern physics, did you see some physical processes? Yeah? Yeah, radioactive decay. And then if you think of this as time, tau as time, do you remember what they would call this parameter in front of time? This will be proportional to something which we would call half-life, the half-life, exactly. So physics is full of cases like this. For harmonic oscillations, this e to the minus gamma times tau, or e to the minus 1 over q, is something which we will encounter in oscillations, we will encounter it in decays, and so on and so on. So physics is full of exponential behavior. And since we now said that here we made a kind of link with the half-life, you could think of this Q as something which is related to the decay time. And this is actually what we are going to see now. So if you look at the expression here, you also have to keep in mind that the argument to any function, the argument has to be dimensionless. So if tau is dimensionless, our case Q also has to be dimensionless. But if tau had been time, then Q has also to be time, have to have dimension time. So Q plays the role of a kind of decay time here. So let's see how we can analyze that and try to express this Q in terms of the way a system is going to decay or the motion is going to come to rest due to the damping or the friction term. So let's take a quick look at that. So if we now go back to what we had, we know that there is there's a driving period which we defined, and this is without an applied external force, without this force F of tau. Now we're just looking at the motion which is being damped. So if we go back then, we know that there is a period, driving period t, which is given by 2 pi divided by the natural frequency. So this will be the driving period for a damped motion. And then if we now go back to what we had, so we assume that beta is much, much smaller than omega 0. We have that this quality factor is given by omega 0 divided by 2 times this parameter beta, which now contains the friction parameter and the mass. Then what we can do is actually to rewrite this factor which we have in terms of pi. So we have a 2 pi here, and we have the 1 over beta. So I'm just putting in the definitions here, divided by a 2 pi of omega 0. And we would simply call this as a pi times the decay time divided by this period. So this is actually the Q value. And this Q then, what it represents is the number of periods in the decay time. If we think of this Q as a decay time here. Or we could actually rewrite it as pi multiplied with the number of cycles which you perform cycles or oscillation performs in one decay time, in our decay time here. So our oscillation makes in one decay time. So just to quickly remind you of what we may have, if you go back to the case with underdamping, this is where this is very clear. So we had a solution which was given by 1 minus 1 over q of tau, plus some kind of sine or cosine motion here. So we would see something like this. We begin at a time t0, and then it would go like this, and it could cross the axis, and then it would oscillate a little bit, and then at the end it comes to rest. So what this decay time actually accounts for is a number of typical oscillations we will be making before this comes to rest within one decay time here. So it's a way to actually link what we see when we solve the equations with the physical parameters of the system. So this parameter Q, which we have, is a parameter which is now given by the physical parameters of the system. So this omega 0, just to remind you of that, is a K divided by M. Beta is simply the friction or the resistance parameter divided by 2 times the mass. So what you see here is that Q is given by the physical parameters of the system. So the way this system is going to behave is now, or the way it's going to decay without any external force which apply, is going to be governed by this time Q, which we interpret as a decay time. So this is a kind of additional interpretation which you can make of the results which we have seen till now. So any questions so far? Okay, I would like now to move into another topic which is relevant for homework number 7. And this is about the mathematical pendulum. And after we've done with that, I'm going to say something about Fourier analysis, which is an extremely useful tool, which, however, we will not deal with too much in this course. I mean, I just want to mention it because you're going to meet it again and again and again. And it's also a powerful way to solve differential equations, whether they are ordinary differential equations or partial differential equations. But let's switch back to the whiteboard here. No, not the whiteboard, to the slides here. So I'm going to take the liberty of just going through some of the derivations by looking at the slides here. There's one thing which I'm going to make a small video of, so you can actually watch that video. So there is a additional section, and we are going to discuss this a little bit later as well. When you solve differential equations, what we have done till now, since we have been totally obsessed with energy conserving forces, we've been looking at Euler-Chrömer and the velocity-Valère method. These are methods which conserve energy. And you probably saw that when you worked with the midterm, that if you were to apply Euler's method, you would not conserve energy. Now, there are powerful methods which have a very good mathematical approximation in terms of the time step, which are called the Runge-Kutta methods. Have you guys heard of these methods? So there's a whole family of methods, and they deal with the way you approximate an integral when you want to solve a differential equation. So let's look at some of the details without going too much into the details. So the basic philosophy here is that they provide you a recipe for calculating with a mathematical error, which goes like the time step to the power of 4, which is much better, or twice the approximation which the velocity-Valère method makes. However, these methods do not conserve energy. So if you are going to apply the Runge-Kutta family methods to the calculation of, let's say, the energy of the Earth-Sun problem, you would see that these methods, even if they have a great mathematical approximation, they would, after many, many time steps, they would actually not conserve energy. But these methods are used in the systems like those which we've been studying now, with harmonic oscillations. And remember now that when we do harmonic oscillations with a resistance term, we are dissipating energy. So we do not conserve energy for the isolated system. So energy is lost to the environment. And since we are just looking at the isolated system, we are now having a system which by itself does not conserve energy. So this sounds like something which is not so nice. The thing is that if we were to model how energy is transferred to the environment, we would actually need a complicated way to link the system with the environment. So the kind of price we pay is that we have a system where energy is not conserved. And then we would like to look at the time evolution of this system. And the reason why we then use these Runge-Kutta methods is that these methods have a high mathematical truncation error in the time step. So that means that they are in general pretty stable for the systems which we are looking at. So if you're simulating a pendulum or an oscillatory motion, these are the standard numerical methods. So when you took CMSE 201, and some of you may have taken CMSE 202, you've probably been calling a package which solves differential equations, right? And into that package, you will find an acronym, which goes like RK2 or RK4. And these are different approximations of the Runge-Kutta family of methods. So what we are providing you with are the codes for doing this. So you should feel free to use them as you want. In addition to the Euler-Chroma, the velocity-Valais, or just Euler's method. So that means that you will have a kind of baggage of programs which you can use to solve these type of problems. When I say these type of problems, this means typically differential equations which arise in mechanics. Or it could be in waves and motion, it could be in electromagnetism, or in quantum mechanics. So let's take I'm just going to bring up some of the formalism here. So what you're doing now, if you look at the equation number 1, when you integrate it up, like we did for a falling object, we actually integrated up something like this. And then we have an integral which we have to solve. So these methods, they come from the way you approximate the integral. That's their mathematical basis. So then there will be different ways to perform an integral numerically. So probably you heard about the trapezoidal rule. Does that ring a bell? And some of you may have heard of that. There is another rule, which is called the Simpsons. No, it's not the Simpsons family. That's the Simpsons rule. That's another famous method for integrating an integral. And these methods, they allow us now to define in a pretty, so the way you approximate these integrals defines then the accuracy of the method. So one of the methods here, which is called the rectangular rule, gives an approximation which goes like delta t or h, which is the step size, to the power of 3. There is another method, which is then called the RK4 method, where you actually integrate an integral using Simpson's rule, and that gives a global error which goes like the step size to the power of 4. So if you think back to the velocity-Valais, that had an error which went like the step size to the power of 2. So this is a clear improvement to that method, but it doesn't conserve energy. So keep that in mind. So if you're going to apply this method to the Earth-Sun system, this method would actually fail in conserving energy and in conserving angular momentum and linear momentum. So what you will find in the slides here is a continuation of what Julie discussed. And we're actually going to have a discussion of that a little bit later. not next week, but the week thereafter, on how you can actually bring in all these methods in a class, a solder class, so that you will have a kind of your own set of methods which you can use in order to study this type of differential equations. So as you can see here, I have defined something which I call a forward Euler, so just encoding the method. But then I have defined a force here. And this is a kind of force you would apply for different types of systems. And then you have the methods as generic methods, which you can just call and use as you want, depending on the kind of situation which you have. So what you see here is a collection of these methods. So you will find the Euler chroma, there's the velocity Valais, and there's this Runge-Kutta to second order. And then there's one, or the more popular one, which is the RK4 method. That means that you can just set up the basics here with a time step, the initial conditions. So this is a one-dimensional problem, initial velocity, initial position, the force you're applying, and then you transfer the equation for the force. This is a spring force, and you transfer that one to the method, and this simply solves everything for you, as you can see here. Now, one of the things which I wanted to move to now, which is linked with homework 7, that means next week, and that's another example of harmonic oscillations. So the mathematical pendulum, as we derived, I think we did it 2 or 3 weeks before spring break, it has, without any damping, it has a term which goes as a function of the angle. So this is the acceleration, the angular acceleration. And there's a term which goes like the mass times the gravitational acceleration times sine theta of the angle. So in this case, we don't have x and y and z, but we have the angle. So this pendulum is just rotating on a swinging back and forth. Then, in the same way as we did for harmonic oscillations with a spring force, we could now add a term which depends. So we have the velocity, which is simply given by the change in the angle, right? Multiplied with the length. So that would be the velocity which we have here. And then we can add a term which now contains the, so we have an acceleration here. And we can add a drag term where we have put in the air resistance or some other complicated forces which are at play. So we are modeling now the air resistance in terms of something which depends on the angular velocity multiplied with a constant. So this is pretty similar to the harmonic oscillations we've been studying now, except that in the previous case, we had a linear term in the unknown quantity x. Now we have something which is nonlinear. Now, this case, you can actually find analytical solutions for small angles. But if you want to deal with a general angle, you don't have analytical solutions anymore. And that has simply to do with the fact that you have a nonlinear term in this sine theta. So this is an example of a nonlinear differential equation. Then you can add a driving force, as we've done before. So this could be a sine force, it could be a cosine or whatever. And you could make the equation a little bit more complicated. And you would end up with a term like this. The next thing you would do is simply to get rid of the constants, like we did before. We would scale the equations as before. So you would now divide by m and l on both sides. That means that your natural frequency now would be the square root of g divided by l, instead of k divided by m, as we had before. So this is just another way of, how we should say, massaging the equations, and then try to transform them into something which is simpler, and which we then can render in terms of a dimensionless equation. So it's a same kind of exercise, and we do that irrespective of whether we are seeking an analytical solution or a numerical solution. So that means that when we introduce a new frequency, we have the same dimensionless driving frequency And then we have the quality factor, but now it contains the gravitational acceleration. We have a dimensionless amplitude. And when we put everything together, this is the new equation. And it looks pretty much like the one we had before, right? Except that now, instead of x, we have an angle theta. We have the quality factor, so we just rewrote the equations in terms of that. But instead of a linear term here, we now have a non-linear term in terms of sign. And that's the one which gives a much, much richer set of solutions. Actually, this pendulum is one of the standard cases if you're interested in chaotic motion. So the next homework has actually an optional exercise where you can study chaotic motion if you want to do that. That's a small challenge and it gives you some additional points. But the same kind of oscillatory motion is something which you will see here as well. And then you can rewrite everything in terms of two coupled differential equations, and you would solve them numerically. So what you would do then is to solve these two equations. So now your acceleration, which is this term here, is given by these new terms where you have a sine term instead of a term which was linear in x, or would have been linear in theta. So if you have a very small angle, theta, you could replace sine theta with just the angle theta. And then for the case of no damping, you have analytical solutions. And also with the case of damping. So you could actually have repeated, if you look at small angles, you could have repeated the same exercise, which we did with a plane block, which was sliding back and forth on a plane. Any questions so far? So I just wanted to show you the connections between different types of systems, but all the systems are governed by almost the same type of differential equations, and they lead to an oscillatory motion. So if we now look at the solution here, we can now define a pendulum force, which now contains this nonlinear term. In our case, we have a sine of x. We have a force, which is a cosine x, or cosine. And then we can now simply just set up everything. We set up a delta t, 100 years. This should actually not be years. This is a copy and paste from the gravitational problem. So this could be dimensionless time. I didn't see that before now, actually. And then we have a theta 0, the initial conditions. We have a velocity, which is 0. We set a parameter gamma 0.5. But now I'm going to put this one back to 1 here. So this is the force which I'm applying. So I have a scaled frequency, which is just 2/3. So if you run this, what we will see is something which we have seen before, right? So if you look at the beginning, this is where we have the transients kicking in. So that's when we have the damping factor, which is trying to correct the system or dampen the system. But then we have the applied external force, which after some time kicks in, and then we get a standard regular motion, right? So this looks pretty much the same as what we had before. Now, one thing I could do now, I could change this external force, and you're going to notice something quite interesting, which for those of you who are interested in exploring in the next homework, actually leads into this interesting field of chaotic motion. So this is an optional part, actually. And so if I only change the applied force, suppose I put this one equal to 1.44, right? Like this. Huh, look at this. That looks strange, doesn't it? So I'm going to leave this as a kind of exploration for you guys. But this is a typical signal of something which hints at what's called chaotic motion. If you're interested in studying that, that's a very active research field in this type of harmonic oscillation type studies. So it doesn't give us what we would expect from what we have seen before. Now, the thing I wanted to switch to now, and which is going to be the last topic on harmonic oscillations, is this topic about Fourier transforms. And this is an aside. This is also an aside, actually, but I wanted to give it to you as a kind of teaser. If you want to explore it, there's actually an honors project which uses this homework number 7 and allows you to go into the studies of chaotic motion if you're interested. But the reason I wanted to mention the harmonic oscillations is that if we now go back to this example I mentioned of washboards. You remember that example we discussed on gravel roads? You've probably seen that. Actually, the formations of these washboards is an active research field in physics. So people have dedicated their lives to study why you get washboards on gravel roads. It's actually a lot of interesting physics, and you can take a look here. I think I have a reference here somewhere. So this is a scientific article which was written some years ago, Dynamics of Granular Ripples Formed by Rolling Wheels. And you can actually show that depending on the speed of the cars which pass this gravel road, you can form washboards or not. So there's an interesting application of what we normally call micrometer level physics with interesting applications of friction and actually mechanics. So if you're interested in that, we actually do have people who do research on that at the Department of Physics. Now, what I wanted to use this one in connection with Fourier analysis is that the Fourier analysis allows us to parameterize or to make a model for the kind of force you will feel when you pass a washboard. So let's take a look at that on the whiteboard. Because if you look back at what we did till now, we applied a force which had either a cosine or sine. In real life, it's not very likely that you can have such a force. So let's try to look at the case of this kind of washboards and why Fourier analysis can be of interest for us. So let's go back to the whiteboard. Okay. So let's bring in this topic of Fourier analysis. So if you now look at just the example of a washboard, let's take that one. That's just one example. And I'm a little bit addicted to this case because I often ride with my gravel bike and I often hit a washboard on a gravel road. So what you might have is, suppose this is your road, then suddenly you will actually see pretty regular patterns like this. So that scientific article which I pointed to is an article which tries to explain why you get this kind of regular patterns. So if you look at something like this now, it could look something like this. Now you have a moving object and you would like to model a force based on this shape, because this is going to be the kind of things you're going to roll over and that they are going to impact your motion. So suppose now you would like to have a force which you want to deduce from this expression here. What you see is that it looks pretty periodic. So we are going to make an assumption now that this is the same after a time t. So this is the period. This is an important assumption. Okay. So you could cook up some kind of mathematical shape for this kind of force. Or you could say now that since I have something like this, which is periodic, can I actually approximate this with a series of cosines and sines? Because then the cosines and sines, they are useful mathematical functions. And we know how to calculate with cosines and sines. So we know their properties, we know how they behave, There are lots of nice trigonometric relations which we can use. So what comes now is actually Fourier's theorem. So Fourier's theorem says that you can expand any periodic function in terms of a cosine and sine series. That's an extremely powerful theorem. So Fourier's theorem, I'm just going to write this like this. So we can actually expand this in terms of a series. And this series is actually going to look like something like this. So there's going to be a sum from n equals 0 to infinity. There will be a coefficient, which is an an times a cosine of n times some frequency times time, plus b of n of sine of n of omega t. This is actually Fourier's theorem. So we are not going to prove it. If you are interested in real analysis, and I know that some of you are, you will actually see a proof of Fourier's theorem. We're just going to use it. So Fourier's theorem is an extremely powerful way to approximate functions which are periodic. So if you go back to this favorite situation of mine with a washboard, I could now actually think of using Fourier's theorem to make a mathematical model for this washboard. Or it could be any other things which has a kind of regular pattern. So for those of you familiar with electronics, you know that you have something like a square well signal. You may have seen that. So another type of signal is something like this. It just repeats itself in regular patterns. So it has a specific period, etc., etc. I don't know if you've seen these kind of connections, but this doesn't sound intuitive. So how can I actually approximate something which looks like that with a sine and cosine? This is the strength of Fourier's theorem. So what I wanted to give you is actually a kind of bird's view on these things and how you can use them to model a specific force, because often you don't have a proper way to model it. You may just have some kind of shape which you are deducing some mathematical expression for. But with Fourier's theorem, you can express it precisely in terms of cosines and sines. And you can mathematically extract these coefficients an and b of n. Now, one question to you before we move on. If you look at cosines and sines, they are polynomials, aren't they? If you go back to exercise, the first homework, you made a Taylor expansion, right? So they went like x squared, x to the power of 4, and so on. If I calculate the integral, there's another thing with a polynomial. So cosines and sines are actually polynomials. So if I were to assume now that x lives between minus pi and pi, and I'm calculating the integral of minus pi up to pi of, let's say, a cosine of n times x times a sine of n times x of d of x. So we said that sines and cosines are polynomials in x, and they are polynomials in x to infinite order. What do we call this kind of polynomials, which have, as a result here, the roundest number in the world? So that integral is actually equal to 0. I'm just anticipating here. These polynomials have a name in the literature, in the mathematics literature. Have you met some of these examples? Have you heard of orthogonal polynomials? Not all of you have taken linear algebra, but these are polynomials which are extremely powerful, because if you have a set of polynomials which are orthogonal, you can expand any function in this set of polynomials. So there are some extremely powerful theorems in mathematics which allow us to approximate tricky functions with some simpler functions. So the whole basis for this Fourier analysis are actually properties like these integrals. So sine is a anti-symmetric function. Does that say something to you guys? And cosine is a symmetric function. So when you have a symmetric times an anti-symmetric, it becomes anti-symmetric. When you integrate it, it becomes symmetric. So what you have now is two symmetric pieces around zero, and they cancel each other. So that's an intuitive way of thinking of it. So on Friday, I'm going to sneak in some 10 minutes on trying to summarize this piece and show you the beauty of Fourier analysis on studies of harmonic oscillations, because this is a topic you're going to meet many, many times. And it's an extremely powerful tool in order to analyze this kind of physical situations. But it's not going to be something we are going to ask you about in the midterms or the finals or the exercises. I just wanted to have this as a kind of digression for things which are coming. So have me excuse for that. But I think it's important to show these kind of digressions and their role in science. Okay, I'm just going to hang around till 5. We're going to switch off the recording. Feel free to ask questions as always. So for those of you online, I'm going to stop the recording.